All right, hey everybody. I have a very quick video for you for this one. Now that we have introduced our principal curvatures, kappa 1 and kappa 2, it is time to introduce two other super important measurements of curvature, the Gaussian curvature and the mean curvature. So if we are looking at a point on our surface, we're looking at a point S, and we're able to calculate the principal curvatures kappa 1 and kappa 2, then we can also calculate the following two expressions. First, we have the so-called Gaussian curvature, which we denote with a capital K. The Gaussian curvature is simply kappa 1 times kappa 2. So it's our two principal curvatures multiplied together. Second, we have the mean curvature, and the mean curvature, which we'll denote with a capital H, is just going to be the average of our two principal curvatures. So it's kappa 1 plus kappa 2 divided by 2. So mean in this case really meaning mean as in average. So with these two introductions of these two curvature expressions, we now have two other ways to measure curvature at a point by computing a single value. In this case, single value capital K. In this case, single value capital H. I'll end this short video with a fun fact, right? And this is fact due to linear algebra, let's say. The way that we computed our principal curvatures were to solve that eigenvalue problem involving the differential of the Gauss map, right? So that dn sub p. Because the solutions kappa 1 and kappa 2 were the solutions to that eigenvalue problem, it turns out that we can represent the Gauss map as a matrix that involves the numbers kappa 1 and kappa 2. And without going into the details in this video, we'll save that for linear algebra exposition, this means that the kappa 1 times kappa 2 will end up being equal to the determinant of that differential of the Gauss map. So Gaussian curvature is equal to the determinant of this matrix, while the mean curvature is equal to the trace of this matrix. Finally, because of the way determinants work, right? I should say, according to our Weingarten equations, the dn sub p, that matrix, was just the inverse of our first fundamental form times our second fundamental form, right? That was the Weingarten equation. So because of how determinants change under matrix multiplication, the determinant of this is nothing more than the determinant of our second fundamental form divided by the determinant of our first fundamental form. And we have now a really slick way to calculate our Gaussian curvature. There's no corresponding slick equation for our mean curvature, but taken together, these observations can be used to calculate these two very, very important curvature measurements. Super exciting. Awesome.